So very big fabrication, large structures, and so I did that for 3 years. Decided I wanted to go back and take an academic job, and so I got a faculty position at Mississippi State in '94, and I was there 22 years and came to Alabama about 9 years ago. Yep, so we're going to talk about metallurgical engineering, and I'm this year trying to pique your interest. Hopefully some of you will consider coming to Alabama and getting your engineering degree in metallurgy, and that will put you in a position to be a welding engineer out there. And welding engineering is something we need in this country desperately. I was talking with some Navy people just a few weeks ago, and the Navy recognizes that in the United States, we don't have the forging and foundry and welding capacity that we used to have, and we need to get that back. And so the Navy wants to make 6 submarines a year. Right now we're averaging about 1.2. You know, we're woefully behind in terms of people like you who can get out there and get things done. And so the country needs the kind of things that you're doing, and so that's actually pretty exciting. So I'm going to just talk about metallurgy a little bit, but before I do that, does anybody have a question for me? I've never been to Shelby State before, so this is kind of a new thing. I'm not really sure how I fit in, so I'm just up here winging it a little bit. And if you ask me some questions, that's going to make my job a little easier. So it's hard to talk for 2 hours. Yes, sir.
Okay, what did the curriculum look like from Arizona State where you were taking would you say welding technology?
It was a welding technology program. Welding engineering technology is what they call it.
Okay, so you're transitioning from the mechanical skills of welding and learning more about the science and of the materials. Was it heavy on material science?
Let's say that again.
Was it really heavy on material science and learning about different types of metals?
Well, no, you're asking something from 1982, right? So I'm pausing here a little bit. It was engineering technology. What that means is when you take physics, it's not calculus based. That's why it's not engineering. It's engineering technology where they transition the math slower to let you adapt more easily. The program, the engineering technology program, was heavy on metallurgy, and it was heavy on the electrical side of things, the power supplies. We did some, what did we do? It was a long time ago. We did some lab work where we are measuring thermal cycles in a welded plate, and we did some theoretical calculations of the thermal cycle to compare we did some experiments to see how accurate those equations were. I don't know if you're familiar with Rosenthal. There's some math out there to predict peak temperatures and thermal cycle and cooling rates, and so we try to validate some of that stuff. Yeah. So we got a taste of that in junior college at the community college level, but the taste is just a whole lot deeper at Arizona State. And I don't even know if that program's still there. It was quite a while ago, but an engineering technology program again just tries to bring in the math burden a little bit slower, let you digest things a little bit more easily. I think there was another question over here or back there.
What specifically did you do at your job before you started working at college?
Well, so Babcock and Wilcox was my employer. Babcock and Wilcox is one of the things they do is build big pressure vessels for Navy ships. So these big boilers, 10 feet high, 4 feet in diameter, a foot thick, big massive structures. So we fabricated those. And what I did was most of my work there was on weld distortion. So the Navy's pretty precise about tolerances and as you know, if I have a structure that needs to follow tight tolerances, and I'm welding, but I got a problem. And so there's a lot of weld distortion kinds of predictions we were trying to do, to help in the shop and get deal with the distortion. You know, you've got that welded structure, it's got all that residual stress, you start machining on it, it moves all over the place, right? And so you really, that's mostly what I did. And then, Babcock and Wilcox at the time was owned by another company called McDermott. McDermott is offshore structures. So I spent a lot of time in southern Louisiana, where one of their fabrication facilities was. We were doing a large offshore structure for Shell, and they were also having weld distortion problems. Yeah, so I was down there trying to help them deal with their distortion problems as well. So, welding distortion doesn't always get the attention it needs. It's kind of a big deal if you have any kind of tolerances to play with, or that you have to abide by. Yeah, so, the guys at Shell, or rather, the people at Shell that were our customer, the Shell people asked the McDermott folks to make a structure with tighter tolerances than the McDermott folks were used to, but they didn't really have enough knowledge to know that was going to be a problem, so they bid and got the job, and they realized they're spending more money on moving distortion than they spent welding it to begin with. They're losing money hand over fist big time, because they just didn't appreciate the fact that those tighter tolerances were going to be hard to hold with all the welding that was going on. Yes, sir.
What different degrees did you program over, and what's like the time investment to this?
So I can offer you a bachelor's degree in metallurgical engineering, and I'm unclear about how much of the coursework you have here translates. I've never had a student from this institution transfer, so this is all new ground to me. I don't know how much of what you have transfers in. It's a 4-year program, if nothing transfers in, but I don't think that's the case. So I can give you a bachelor's degree in metallurgical engineering, and that gives you good exposure to metal science. On campus, we're one of a few schools in the U.S. who has a very active and functional foundry. So we pour metal. We take big buckets of metal and melt it and pour it into sand molds. And so that's one of the things you get exposed to in the program. We make you an expert in how metals, why metals do what they do. So some of you are doing welding, and sometimes welds crack, and there's a metallurgical reason for that. So you learn some of that metallurgical science. You're going to learn why hydrogen's bad. You're going to learn what to do to avoid cracking in a weld with a high-strength steel. We're going to teach you some of the science, and we're going to, along the way, try to dispel some of the folklore. No, your welds don't get stronger if you spit Copenhagen on them, all right? I don't care what your grandfather told you, it's not the way it works. So there is a lot of folklore in the welding world, yeah, and so one of the things we try to do is dispel some of that, all right? Yeah. Yes, sir? Metallurgical. Metallurgical. Yep. So that's metal science. Yep. So they don't call it metal science, they call it metallurgical engineering. Yep. I don't know why, half my students are girls, so it's definitely not a boys club. I got about 81 students, and I think literally 60% are female. We are a little different from other engineering because we live in two worlds. We live in a macroscopic world, just like you live, and we also live in a microscopic world. We're the first, we look at metals under microscopes to understand why the metal is doing what it's doing. And so that makes us a little different and maybe a little more sciencey. Maybe 3 or 4 months ago, there was a barge outside of Baltimore that crashed into a bridge, and that bridge collapsed a little too easily, all right? So a metallurgical engineer would take a little sliver of that metal bridge, go back to the lab, put it under a microscope, and that metal's gonna tell me a science-heavy story about how it was processed, and so we can verify whether the metal was processed properly, and that's part of some forensics, right? A metallurgical engineer gets on board when a metal thing breaks, and we try to figure out why it broke, and so there's some cool forensics things that we do. I probably get a phone call from a lawyer once every 2 or 3 months, you know, there's been an accident, the metal thing broke, somebody's been hurt. If I give you the metal part, can you tell me why it broke, all right? So we do some forensics, and that's cool stuff. We also do advanced manufacturing. So I don't know if you're aware of this or not, but the next big thing in the metals world is going to be metal 3D printing. And we have, in the last 3 or 4 years, we have purchased 2 things you need to print a metal part. You need a printer and you need ink, all right? And so we have an ink machine, which is a machine that makes metal powder. That's my ink. And we have a metal printer, and that metal printer uses that powder to print metal objects. And so that's going to be the next big thing in the metals world. And the University of Alabama will try to play a lead role in that capacity. So there's only probably 6 or 7 schools.
So I'm a machinist by trade, so I don't really understand all the welding technology, but I mean, we weld aluminum,
Yes.
we weld steels, we
Yes.
weld stainless,
Yes.
and those materials have different atomic structures, like body center cubic and face center cubic. And so what is it about certain metals that you can't weld? You have to wind up with brazing it or something like that. Why is it there's certain metals that cannot be welded by a traditional process? Whereas, we have all these different, like aluminum is a very different metal than, steel.
Yeah.
But both of those can be welded. But there are metals that don't lend themselves to welding. It can't be just atomic structure. It's got to be some other factor.
Yeah, so let's talk about steel. Some steels can be welded and some not so much, right? And so, but they're still steel. And so, a high strength steel, when it's cooled quickly, like the cooling that occurs during welding, when it's cooled quickly, the alloying elements give me different phases of when a weaker, more structural steel as well. That's not making a lot of sense. I've got 2 steels, and one of them is going to form different structure during solidification than the other, and that different structure is going to give you the lack of strength and the brittleness and the cracking susceptibility. So I'm trying to speak without using metallurgical jargon. Do you know what martensite is?
Yes.
Okay, so that's what I'm talking about. A high-strength steel, when it's cooled quickly, is going to form martensite, and that's going to make me prone to cracking. And then if I've got an 836 steel, I'm not going to get that martensite. If I do, it's going to be very much less hard than the higher strength steel. So I'm going to get different mixes of I'm going to get martensite versus pearlite and ferrite.
So the whole idea here is not that it can't be welded, but the welding is not going to be successful because of the way the cooling is happening and the alloy content and things like that.
Yes.
So high carbon's a problem
Carbon's a big problem.
so the higher the carbon content, the more difficult it is to weld.
Absolutely. You're going to be much more prone to some martensite formation as you crank up that carbon content.
For material like, I know this because I know it, not because I weld it, but like 304 forest stainless.
Yep.
You can get an L version.
Yep.
Well setter. And what is that? Is that a
It's low carbon.
low carbon?
Yeah, and that's primarily because that's an austenitic stainless steel, and when you weld on it, you're going to get, if there's carbon in there, it's going to combine with the chromium on grain boundaries, and you're going to deplete an area along that grain boundary of chromium, and now those grains might fall out. And so you need low carbon so that you don't form chromium carbide and steal chrome from the grain itself. So that the element is low carbon. As an austenitic stainless steel, you're not going to get there's no martensite being formed. It stays austenitic all the way down from elevated temperature to room temperature. You just need to get the carbon out so that you're not going to have that grain boundary.
And the nickel is acting as austenite?
That's correct. Nickel does the austenite promoting, and then chrome does the ferrite. I think I'm getting that right. You have chrome and nickel, they're doing the opposite things. One giving you ferrite, one giving you austenite, and I'm starting to wander away from my area of comfort. Yeah. And some things just can't be welded. You know, I went on Monday, I went to Huntsville and recruited, and I was at the Rocket Center. And I don't know if you've been there before. I've never been, but they've got a lot of, NASA hardware in there. And they've also got a V2 rocket. You know what a V2 rocket is? Who knows what a V2 rocket is? What's a V2 rocket?
It's the rockets, the Germans,
Yeah, so they're shooting rockets from France or Germany or wherever at London, right? They're the first people to have these long-range rockets. And so they have one of those rockets in the Rocket Center, and it's a little bit dimpled and dented, and it's no welds, it's all riveted, all right? I'm not sure why that is, but the airplanes today are almost all riveted. There's no welds on a commercial airplane because the aluminum alloys they use don't respond well to welding. So some aluminum alloys you can weld, some you can't. And the aircraft grade aluminums that have the strength that they need, weldability is not good. So you still see rivets. You might think eventually we're going to be done with rivets. It seems pretty barbaric, old school, but yeah, they're still out there.
One of my former students worked on an aircraft carrier as a I don't know what they call that, repair guy. If they have any kind of structural damage to that plane or anything needs to be repaired.
Yeah.
And he said those rivets, the skin of the aircraft is aluminum.
Yep.
He said the rivets would come in packed in dry ice. They were going to put them in cold.
Okay.
So they put them in cold, and then when that plane is moved out to the flight line or out on the deck, with it heating up, it actually makes that rivet harder.
Stick it in there harder.
Yeah, it actually strengthens up that rivet after they put it in.
So if you open up a material science, so going back to World War II now, Germans had some pretty sophisticated engineering. That V2 rocket, that's something that the U.S. did not have. The Germans developed the first jet plane towards the end of the war. We didn't have one of those either. Their tanks are better than ours, so those guys do some good engineering. And one thing the Germans also had at the beginning of World War II was submarines. I talked to you about making submarines. The Germans had a lot of submarines, and they were terrorizing ships leaving the U.S. and going to England to drop off supplies. And so these Liberty ships were the first welded ships to be mass-produced, and they had some welding-related problems, and some of these things were cracking catastrophically. And if you open up any material science book, somewhere in chapter 1 there's a big picture of a fractured Liberty ship, because we didn't do a good job with our welding consumables weren't very good at that time, and we didn't have the knowledge we have today. So that transition into welded ships didn't necessarily go very well, and you always see that documented in a material science book. But what you don't see documented is, those ships were breaking because the welding technology wasn't very good. But those ships were also getting shot at by German U-boats, right? Shooting torpedoes at them. And those I went to Chicago for one of those foundry visits. There's a museum there where they have a German U-boat inside a building, believe it or not. And there's lots and lots of wells on that ship, on that submarine. Why don't I ever hear about German submarines breaking too? Because I sure hear a lot about Liberty ships breaking, and these are occurring at the same time. Those U-boats are being fabricated. So we're making our Liberty ships. You know, what's different about a sub versus a ship? I don't have an answer. But that's a bit of a mystery to me. All those submarines were stick welded, and the welds looked pretty good, but they didn't look like magically good. So I don't know if the Germans had trouble with breaking and they just kept it to themselves and didn't advertise it, or they were dealing with a better steel than what we had. I really don't know the answer. But we had a lot of Liberty ship failures that we still talk about, and we don't talk about U-boat failures. Yeah, weird stuff. But I did learn is, so when those submarines, those German submarines needed maintenance, they went to shipyards in France, because France was occupied by Germany. And so the French workers would drill holes in the submarine where they knew oil would leak, and they'd fill up the hole with wax and then paint over it. And then once that sub was out in the ocean and the wax came out, then oil leak would ensue, and an oil leak is the only really reliable way for you flying an airplane to locate it where a submarine is. And once it's underwater, you can't see it, but you can sure see the oil slick that's leaving behind, it's leaving oil. And then they can drop their torpedo bomb on them and, you know, dive bomber and try to take the sub out. So that's a cool story. If you leave me up here long enough, I'll just keep rattling on stories. You know? I would not want to be inside that German submarine. It's pretty cramped. Yeah, that's not good.
Any submarine is like that.
Well, I guess, yeah. So I guess I'll wrap it up. I'll reach out and see if we can organize a family trip. Yeah, I think you'll be impressed by that, and it'll give you a chance to visit campus, and maybe give you a chance to go check out Bryce Hall. Really, really super awesome. Yeah. Good. I'm going to leave you with a handful of business cards, and if any of the students, he's going to have some of my cards. If any of you want to reach out with an email, I encourage you to do that. If you want to come to campus sometime and get a tour of some of the equipment that we have, you're happy to do that. I do it all the time. You want to do that? Yeah. So he's got my card with an email address. I don't really answer the phone, that's on that card, but I definitely answer email. And so be happy to chat with you and organize a visit if that's what you want to do. Yeah.
Any last questions to wrap up? We want to thank you, sir, appreciate you taking time.
Absolutely. Yeah.
And we'll see if we can't come on Foundry and maybe a little field trip.
Yeah.
See your laboratory.
Absolutely. Yeah.
Thank you so much. Appreciate it, thank you.
All right. Thank you for your time. In the United States, I can make metal powder. Making metal powder is an explosion hazard, so most people don't want to deal with it. But we have that capability, and we're pretty proud of that. That was a $700,000 investment from our dean, and we just got a printer about 2 weeks ago, and that was about another $450,000. So I'm going to pass around a little, what I've got here in my hands. And you can't see it, but when it comes by, you'll see it. And I do need this back, so don't steal it from me, please. I only have one. This is a titanium bottle opener that was 3D printed. Just to give you an idea that this is real stuff, all right? So you're going to note that the detail, the geometric details is actually very extraordinary. This, if I gave you this, when you see this, if I told you to go to a conventional shop and make me 10 of these, you'd be hard pressed to do it. It's got too much complexity in the shape. So we can print things more complicatedly shaped than we can conventionally machine, all right? It's a big deal. The downside is right now the strength of this is really poor, so there is work to be done. The metal science guys are going to figure that out, right? But that's the future right there for sure. Well, I'll start it here. That's a titanium Ti 6.4, so it's 6% aluminum, 4% vanadium. Yes, sir.
Dennis, is it the sintering process that's?
No, it's not. No, so we start you load the printer with metal powder, And inside the printer, you're gonna spread powder on a flat surface.
So it's powder bed?
It's a powder bed, yeah, and they're gonna melt the strip with a laser. I'm gonna melt a skinny little strip, and then I'm gonna strip powder on top of that, and then melt another strip on top of my strip, and you stack them up. So basically you have that little wrench bottle opener probably has 1,000 little welds in it, you know, and I think all of us know that the welds are weak link from a strength point of view, and if your entire part is made up of 1,000 little welds, you know, no surprise there, strength's not gonna be very good. So we have to fix that.
Now, I'm sorry if I'm manipulating the questions here, but, is that done under vacuum?
No, so there's an argon built chamber, so you're being protected from the environment by inert gas.
So it's acting as a shield gas?
Yes.
What brand machine did y'all purchase?
Acronity, I believe that's correct. ACRONITY, Acronity, I believe that's right.
Now the door on that machine, is it heavy like a bank vault, like thick, sealed really well?
I've only glanced at the machine, we literally got it like 10 days ago. The technician from Acronity is literally installing the machine today and training people today and tomorrow. So I've only got a sort of quick glance at it. It looks pretty beefy to me. Yeah, we decided to do the ink first because at Mississippi State, we have a couple metal printers already when I left there. Auburn probably has a half dozen or more metal printers. They do a lot of metal printing. Nobody around here has the ability to make powder or ink. So we decided to jump on that and not duplicate what our neighbors had, because our initial investment was a powder machine 3 years ago, and then the printer was just very recently. So we're one of the very few schools that can make powder, and then having the ability to do powder and print all in one building is pretty impressive. Yes, sir.
How good of a finish can you get on that process?
Well, did you see the wrench yet? I mean, that's not bad. I think we can do a little bit better, but that might be about the extent of it right now. Yeah.
What all kinds of metal too? What's the extent you have to do that?
We have made stainless steel powder, Inconel powder, carbon steel powder, aluminum powder, bronze powder. Might be it.
Does that machine y'all have y'all say what type of metal you're using, like what powder you're using, and it sets all the parameters to be able to make it? Or
That's
you
what-
have to yourself?
That's a good question. If I tell you if I use the term open source, you know what that means?
Not really.
Okay, so some of the makers of 3D printers keep things secret, right? So they have an aluminum button you push, and it sets all the parameters. And there's a lot of things you can tweak and adjust in a metal 3D printing operation. There's lots of knobs you can turn, and some of the vendors make the knobs unavailable to you and try to make it simple. Here's an aluminum button, here's an Inconel button, here's a steel button. That's all you need to know. And some people are happy with that. Academic folks, you know, we think we're smarter than everybody else. We want all the buttons, you know. And so the Acronity machine is famous for giving you all the buttons, and what that means is it's open source, and they're not hiding anything. You get to tweak it, everything you want that can possibly be tweaked. And so we chose our machine for that purpose, but there are instances where you don't necessarily need all that flexibility. So you know, it's kind of your choice as a customer, how much tweaking you want to let your people have access to. Yeah. So that's a very competitive business, and you know, aerospace engineering folks have probably, I don't know how many billions of dollars GE spent in the last 10 years chasing this stuff, you know, but it's huge. Yes, sir.
So when you're talking about, you guys are actually making the powder,
Yes.
so you have all the different elements, and like, we're working with 4140 right now, tool steel, and we are, you know, it's got 8 different elements in it. So are you actually using those 8 different elements to make that Inconel?
We basically correct. Yeah, at the on top of the atomizer that makes the powder is the big bucket, and I throw in that bucket whatever I want to melt. So I can start with some 4140, or I can start with iron and throw in some carbon and some nickel, you know, whatever I want to get there. I throw into that bucket what I want to melt, and I can make a 5 kilogram batch of powder by taking the liquid metal, by melting the metal, getting a uniform mix, and then squirting that molten metal to it like a shower head, so I have a molten mist that falls through an argon chamber, and that's my solidified powder when that mist solidifies. Yes, sir.
How long is a metal printing process compared to a regular 3D type process?
Well, I don't have much familiarity with the regular 3D printing. By that I mean, I guess you mean plastics.
Yeah.
Yeah, I don't have much familiarity with that. That wrench probably took a half hour to print, the one that's being passed around. Yeah, it's a little slow, and there's a lot of challenges here. You know, we've been welding for a long time, and we know that some metals don't respond well to welding, and the cooling rate's too fast, and we've learned over the years how to control the cooling rate a little bit with preheat, or adjusting heat inputs. We've learned to deal with, for the most part, we've learned to deal with how to make welds in a robust way to avoid cracking due to rapid solidification, rapid cooling rates, okay? Well, this 3D printing, you know, it's kind of like welding. It's a very small laser, but it's much smaller amount of metal being melted, and it's also going at a much higher travel speed than you're used to with welding. So the metal is freaking out in a whole new way that we're not accustomed to. In essence, the cooling rates that the metal sees during 3D printing are much more extreme than the cooling rate the metal sees during conventional fusion welding. And so there's some whole new science we need to figure out if we're going to make this stuff work better. Yes, sir.
So what would be my definition of the 34 metal?
I think last year we were looking at 78,000, 79,000 for fresh out metallurgical engineering. The only engineering at UA, the only engineer who gets paid more than metallurgy would be chemical engineering. They're about 80. So we're all kind of clustered together between 80 and say 65 or 70, but metallurgy is right around 78. Is that what? Well, that's just entry level. That's just fresh out of school with no experience. Yeah. 78 and some change, yeah. There's only I don't know, a dozen metallurgical engineering programs in the United States. So if you become a metal expert and get a metallurgy degree, you know, you're going to be highly sought after because there's only, again, a dozen schools or so who are, training metallurgical engineers. There's hundreds of mechanical engineering programs in the U.S. and chemical engineering and civil engineering and electrical engineering and all that stuff. Everybody's got one of those, but metallurgy there's not a lot out there. So you are going to be highly sought after, and this metal 3D printing is going to make metal more relevant than ever, right? You don't know this, but long ago when I was your age and I was a welding student, people told me what a big mistake I was making because metals were kind of going to go away in the future. And fiber reinforced composites are going to take over the world. And you can't weld fiber reinforced composites, so I don't know what you're going to do for a job. But that's where things are going. And so obviously that didn't pan out like people thought it would. But there's the momentum now behind metals is pretty enormous with this 3D printing. And welding's not going away, and we need more people who know how to forge metal. All this metal working that the Navy wants is something the nation really needs. Yeah. Yes, sir.
I noticed you mentioned the ships. So what are some of the projects that you are working on?
We don't currently have a lot of welding-related projects in metallurgical engineering. So I've been in the department head about 5 years. I'm a welding guy, but I'm the only there's one more welding guy in our department. So we have our projects, we have a little bit of welding, but we have more foundry. Foundry's a big thing for us. We have, projects with the Navy looking at, cold spray. Cold spray is, we're gonna take the same metal powder we're talking about for printing, and then when I take that metal powder and crank it up to about like twice the speed of sound and slam it into the surface of a plate, and it's gonna stick. It never melts anything, so we call it cold spray. The Navy wants to use cold spray to refurbish worn parts, and so we have some cold spray work that goes on. We have $12 million worth of massive microscopes that look at things at the atomic level. So we have some super hard science going on with microscopes. We're dabbling with batteries a little bit. We have a professor who does metal corrosion. Corrosion is the #1 failure mode for metals. Yeah, so that's kind of important. Corrosion is the #1 failure mode. What's the #2 failure mode for metal? But why do metals break? How do they break? Now I'm asking you a question.
Stress fractures?
Well, okay, and specifically a stress that's applied to release repeated stresses. So fatigue. Right? So that's the word I'm looking for. I call myself a welding guy, but I'm also a fatigue guy. And those two things go hand in hand because welds are kind of bad actors from a fatigue point of view, right? So when you apply a stress and remove it over and over and over again, fatigue cracks can form. And so I bring some fatigue research to the table as well. That's extremely important failure mode. Yeah.
So what companies are hiring metal electrical engineers?
So I think I graduated 12 last spring, and one went to Boeing. That might have been a mistake. Yeah. Lockheed Martin, Shell Oil, Mercedes. Anybody who makes things out of metal, which is pretty much everybody. It's metallurgical engineering. Sounds like a narrow little niche, but it's not. Metal is everywhere. And there's not enough metallurgy graduates out there, so a lot of times businesses, hire a chemical engineer and then train them up on the welding side, because you just can't find them. Yeah, but they're out there in great numbers. Or jobs are out there in great numbers. Yeah. If you went down, I know you're an Auburn guy, so I'm gonna pretend I don't have any animosity towards Auburn. If you go down to Auburn, just outside of Auburn, General Electric has a factory, and they print metal fuel nozzles for their commercial jet engines. You go online and look up the GE fuel nozzle, and there's going to be lots of stories there. GE's very eager to brag about they have. This is the first 3D printed metal part that won a commercial aircraft. Right? So they're very eager to brag about that. So you can see lots of conversation about the fuel nozzle, and there's that kind of factory is going to be something we're going to see more of in the future, and that's again all metal science. And it's a freakish place to be because you walk into that factory and there's no smoke, there's no noise, there's no sparks. These machines humming away silently, printing these nozzles. Yeah, it's pretty weird. All of you are used to dirty, stinky, smelly stuff, right? And 3D printing is not that. It's a whole different game. Okay.
I know you spoke on people transfer from 2-year colleges.
Yes.
It's a 4-year degree, so would it be extra 4 years?
Well, I'm not sure. So I've never had anybody come to the department from Shelton State. So the question is, how many of the courses that you take would be transferable? And I don't have an answer for that. I really don't know. This is all a new game for me.
It's been our experience. We've had some machine tool students, CNC students have gone on to do mechanical engineering.
Okay.
And normally, any academic class you took here, of course, math, English, history, any of those courses you took towards your associate degree would of course transfer. But the technical classes typically aren't going to fit into the curriculum for the engineering course. So normally your technical classes are not going to. Now they're going to serve you well, From our experience, our students have been well prepared to take a lot of those engineering classes because they understand, you know, a lot of the principles that apply towards that. Even, you know, helping with physics classes and things like that. But yeah, typically your technical classes are not going to apply towards that curriculum. But your academic classes will. Well, those are all fitting into an academic, you know, type class. So typically, you might be taking some lab classes over there, but they're not what we would consider a technical class. I'm not really trying to teach you a skill, you know, necessarily. I'm trying to teach you theory and, you know, application of those theories. So it's going to be more academic-based classes.
So the process of applying, is it like you just apply, is it like a pool that you have to be selected from, or?
Well, you can go online and apply to University of Alabama and state what your intended major is, and then you'll get accepted. And once you're accepted, then you have access to an advisor, and that advisor, their job is to look at the Shelton State curriculum and tell you which classes transfer and which ones don't, and how much time it's going to take. So once you apply to this university, then you have access to an advisor who's going to work one-on-one with you, lay out a plan, say, okay, here's how many courses we're going to accept, here's how many courses you still need to take, and so here's the timeline. Yeah. So I don't do advising. What professors don't do advising, they're full-time advisors that do just advising, and they know all the details, and we'll walk you through that. Yeah. Now I'll just say this, you know, I came from the same place you're coming from. I did the 2-year degree, the hands-on thing, right? So there is an advantage to somebody who has some actual hands-on skills, who later goes on and does engineering. You have, as he said, those classes, the hands-on that you have will serve you well. You, with an engineering degree and some hands-on experience, are going to be a far better engineer than the engineer who went straight to a 4-year degree and never really got their hands very dirty and with the experience you have. So that experience that you have, or you're getting right now, is invaluable, making you a more productive and useful engineer. I've seen a lot of engineers who aren't terribly useful because they don't have any idea what they're talking about. Everything's on paper, right? And you know, that's just that's an advantage you would have. It's the same advantage I had. I got to do things that other people didn't get to do just because I had some inkling of, you know, how to pick up a torch and actually make a weld, right? Goes a long way. It means a lot to employers. Yes.
How much is your tuition cost?
That's a good question. Should know that. Tuition is about, I think it's about, for in-state, I think it's around $10K a year. There's financial aid available, you know, so not everybody's paying like that. You can get financial aid because of financial need. You can get financial aid because you have high academic test scores. You know, there's multiple paths to get assistance for that tuition. Yes, sir.
American Wealth Society also has scholarships for any type of building engineering or metallurgical engineering that will pay a significant amount of that.
Okay.
So American Wealth Society is another avenue for
There you go.
scholarships.
How much is tuition here?
$141 per credit hour.
Per credit hour? Okay.
When we've looked at it, I think Alabama's normally about 4 times what Shelton is. Typically. I may be wrong on that, maybe all of it.
How many of you have actually visited campus? Okay, fair number. Yeah, it's a special place. You know, if you've been there, you know what I'm talking about. There's some, that campus is stunning. Let's forget about engineering for a minute. That's just a stunning place to be. No offense to Auburn, but Alabama is a stunning place to be. It really is. The buildings are gorgeous. it's clean. It just has a sparkle to it that most schools don't have. Most of you don't know this, but on the edge of campus, we have a haunted mental hospital from 1861. Yes, we've got some history. There's several buildings on campus that are haunted. They had a pistol duel back in the 1800s between two fraternity boys. One of them got shot and killed, and his ghost wanders around Woods Hall. I'm sorry? Bryce is the mental hospital, yeah. Bryce, yeah. Bryce was there, built in 1861 and finally shut down in 2007. Yes, sir. It is, yes, we did. We're in the process of renovating it. The first floor is fully renovated, and that's the new, I don't know who made this decision, but in the past, the Welcome Center, where you would come to get a bus tour, would be in the Ferguson food court. Now the Welcome Center is at Haunted Mental Hospital, first floor. So that's kind of weird, but that's what we do. And if you go and visit that building, you can walk in without an appointment and just walk around and look at the first floor of Bryce Hall. It is stunning. They packed that thing with all this electronics to lure 18-year-old brains, to try to get them to come to Alabama. So if you have a chance, visit Bryce Hall and walk around the first floor, and yeah, it's impressive. Alabama historically does two things really well. We used to play football. I'm not sure if we still do or not. But we also recruit undergrads. There's no expense spared when it comes to recruiting. It's a big deal on campus. We've got kids from California and Jersey and Chicago and Texas. Our footprint's enormous, and most of that is because we're out on the road all the time recruiting. So it's a fun place to be. Yes?
Can you say we could watch the boundary of Steel Ford?
Yeah, so we have a foundry, and a very active foundry. And the first Friday of every month is Open Foundry Day, and the doors go up, and we get some pizza, and it's open for anybody to come and watch. And we're going to be pouring something that day, and it varies. Sometimes we're pouring little fist-sized elephants. Sometimes we're pouring some larger item for a research project. It varies what we're pouring, but we're going to pour something on that first Friday every month. Yeah, and feed you as well. That'd be a nice trip for you to make. If you've never seen liquid metal get poured, it's pretty impactful. It's a big deal. It's really, really scary. It's pretty dangerous. Yeah.
How do y'all melt them? Just a heat furnace? Or?
It's a big induction furnace. We have 3 of them.
No, I've been to Newport. I've seen the electronic furnace.
Yep. Oh, it's something. Yeah, it is. Yeah. Yep. There's a lot of money to be made making metal. Get a job at Newport, get a job at SIPCO. Those guys make some serious money. Yeah.
And I'm assuming Newport has metallurgical engineers.
Oh yeah, they'd hire all of our graduates if they would agree to go work there. A lot of people don't want to work in the steel mill. It's hot, it's dirty, it's super hot. I made the mistake of going to SIPCO during the summer. It's a pipe maker in Birmingham. It's the hottest day of my life. I grew up in Yuma, Arizona. That was the hottest I've ever been. It was hot. It was just soaked with sweat, I don't know how those guys do it, but then they get paid well too. Yeah. Yeah, so there's definitely some good money there.
Hey, do you have anything beyond just undergraduate? Do you have master's degree?
Oh yeah, we have a master's degree in metallurgical engineering, we have a PhD in metallurgical engineering, we also have a PhD in material science. So we have about 81 undergraduate students and probably 50-ish grad students. Yeah, the grad students are always, our dean always encourages us to involve undergraduates in our research programs. So if a professor is going to survive at the University of Alabama and keep their job, they've got to bring in money from the outside to do research, whether that's from the Navy or government monies, wherever it comes from. They have to bring money in to do work, research work, and that's done by grad students, but our dean's always encouraging us to involve undergraduates as well. So if you come to Alabama, you can find yourself working in a lab, maybe doing some 3D printing, corrosion testing, or fatigue testing, or working with microscopes. So there's lots of opportunity to get involved if that's the kind of stuff they're interested in. Yeah. So I'm here for two reasons. I came here just to recruit, because that's what I do, and then I'm also here because Drexel University, Ohio State University, and University of Alabama have teamed up, and we are writing a proposal at the request of the Navy to help with this workforce development, so the Navy can get to their 6 submarines a year. And so our plan is to have some metallurgy-related distance courses during the academic year for people to take, and then in the summertime, have those same people come to Shelton State and get some hands-on. So that's our way of trying to help the Navy out. And so hopefully we're going to move forward with that project. The proposal, I think, is going out from Ohio State today, or maybe tomorrow. So, there's a big push in this country for metals-related workforce development. I don't know how many millions of dollars been pouring into Mobile to the shipyards and the subyards, but this is a big push. You all are going to be part of that one way, shape, or form. Yep. Yes.
If someone's interested in transferring from Shelton to Alabama, what classes would you recommend they get, like certain math classes?
The more math, the better, yeah. The more math you can get, that's really what trips people up more than anything, is math. And I've been down that road myself. When I transferred when I finished my associate's degree and went to Arizona State for my bachelor's, I signed up for physics, first semester. Physics has trigonometry in it. I never had a trig class. I'm in trouble. I'm in big trouble. Big trouble. Yeah. So the more math you can get to ease that transition to tamp down on that punch in the face, the better. Yeah. So I was in engineering technology programming. The physics didn't use any calculus, but it sure used a lot of trig. And I never had any trig. I actually got kicked out of algebra class when I was a sophomore in high school. So I've got a big hole to climb out of, and I'm not bragging, but I think it's not really about how smart you are; it's more about persistence. That's really what's going to get you to where you want to go. And if you just keep on fighting and persisting, you can overcome small obstacles along the way. Yeah. Why did I get kicked out of maths? What did I do? What did I do to get kicked out of algebra class in sophomore year? Passing notes with girls, right? Yeah. It was worth it. It was worth it too. Yeah. What else can I tell you? Who has my wrench? Good. I want that back. Yeah. We're very proud of our foundry, and we're equally proud of all this 3D printing in the future. And I don't know if I can have anything else to try to throw at you.
It would be interesting to go see a pour on Friday. It's actually a week from tomorrow.
What time would that be?
It's like I think it's like after lunch until say 4 o'clock. It's the afternoon kind of thing. Yeah. It's hard to know, give you an exact time when the metal's gonna be ready to pour, because it's kind of depending on what you're melting, you have to do some tweaking and getting the metal to the proper liquid form. It's really hard to just say I'm going to do it exactly at 2 o'clock. Sometimes things go wrong. You have to add some alloying elements and let it cook a little bit longer. It's not a real predictable path on any given day. Yeah. That's sort of the challenge of the foundry, right? It's something you sort of have to do on the fly and adjust as you go and see how things are coming together.
So if we want to go over there, be there about 12:31 to be safe.
That'd be good. I can hook you up with Charlie Monroe. He's the foundry professor, and he's a young, very ambitious and excitable guy who loves the foundry. You know, and so you'll know, what you'll notice when you come to the foundry is there's a special kind of student that loves the foundry, because not everybody loves it because it's dirty and stinky and hot, you know. But if you're a welding guy, maybe you're gonna like that sort of thing. And those foundry kids, you know, they're a special breed. If you've watched, how many folks here watched Forged in Fire? And see, so you guys are foundry people, probably just don't even know it. Yeah, but once you see it, there may be forging in there as well. We have a group of maybe 10 students who are involved in a foundry project every year. So there's a Foundry Education Foundation, and they are interested in the foundry industry, and they give scholarship money for metallurgy students. And every year they sponsor a contest where, okay, the 12 schools in the U.S. who have foundries, let's all agree we're going to pour a Yoda. Okay, we're all going to do a Yoda. And then we're all going to meet in Chicago in November. Don't ask me why Chicago was picked for a November visit. Every November we go to Chicago, where it's really, really cold. And then we get judged, we have a competition, and the 12 or so schools compare and get judged, and somebody becomes the winner. And the next day we have another contest pouring something different. And so there's a very active foundry presence. And I didn't mention this, but if you do go to Bryce Hall, the haunted insane asylum, you look at on the ground level, all around the circumference of the building are a bunch of metal grates about yay high and about yay long. And the original grates are very deteriorated. 1861 was a long time ago. So we used the deteriorated grates to make a new pattern, and we poured, I think, 50 grates. And those are mounted down in that building. So when you see the grates in Bryce Hall on the first floor, that's done in my foundry. Yes, sir.
Where is the foundry?
Behind Hardaway. You know where Hardaway is? Yeah, it's basically immediately behind Hardaway Hall. Yeah. And portions of it are air conditioned, most of it is not. Pretty intense.
So Dr. Daniewicz, I imagine that parking is an issue over there.
Yeah, I can give you parking passes. Parking is an issue. Parking is to be an issue when I go back to campus today, because I lost my parking spot from this morning. Yeah, once you lose it, it's hard to get back. Parking is a real problem. I can give you parking passes and make that an easy thing. I'm sure Dr. Monroe would be thrilled to have somebody come visit. He might even give you one of those elephants they're pouring. It's a little fist-sized element that I give as gifts to people. And the founding professor, Charlie Monroe, says he's going to pour so many elephants that eventually everybody that wants one will have one. And I'm going to tell them that's impossible. People are insatiably attracted to this little fist-sized elephant, right? And so you can pour them all day long for the rest of your life, and it won't satisfy the hunger out there for the elephant, right? Everybody wants one. Yeah. The largest 3D. Well, we just got our printer like a week ago, 2 weeks ago. So the printer will be functional today or tomorrow with some training, but I've never, we haven't had a printer at this point. All we can do is making ink. Yeah.
What's the biggest metal 3D print object you've seen done in the industry? Is it something just still small parts?
That fuel nozzle, that GE mix, is about 9 inches high. Pretty good size. Yeah. If I go online, you can see some really big stuff being printed too. Yeah, there's lots and lots of 3D printing videos online, and people are printing some pretty big stuff. Usually not with powder bed. There's other things you can do. There's other things you can do other than the metal powder with the laser, right? That's one of the more common ones. But we have a machine that, well, let me back up. We have two machines I haven't talked about. We have something called a friction stir welding machine. Does anybody know what that is?
Yeah, we actually went out there and saw that machine. And
Okay. Yeah.
really neat.
So that's welding without melting, and when you weld without melting, you get a whole lot less distortion, you get a much happier metal. So we have a friction stir welding machine. We also have something called, that's like a friction stir welding machine, except the tool that rotates and as you push into the plate and stir metal with, that tool is hollow, and we're running feedstocking to the top, so we're building up a big deposit. And now it's not very geometrically precise like that wrench is. It's kind of like a big blob of metal, but there's no melting going on, and I can do some post-build machining and have a 3D printed part that has a much higher deposition rate than the powder bed stuff we've been talking about. So I can lay down big chunks of metal there. So we have it's called a meld machine. We have that as well. So there are other things out there than just powder bed, but the powder bed is probably the most common thing. Yes.
For the nozzle that you use, what is the benefit that they found making the nozzle compared to something conventional?
That's a good question. So I'm trying to speak succinctly here. On paper, the GE engineers have long known that if they could, if they could make a fuel nozzle that swirled the fuel in a certain way as it mixes with air, as it's ignited, they could increase the fuel efficiency. So on paper, if I could just make a pathway for the fluid, the fuel that followed this complicated path, on paper I can get a better combustion, more efficient combustion and better fuel efficiency. But like a lot of things, yeah, on paper that looks great, but it's too complicated. I can't make that, So there's a story I tell. You can go online and find lots and lots and lots of pictures of that fuel nozzle because GE loves to brag, okay? They're not shy about boasting. I've seen a picture of the fuel nozzle, as you can easily see, but I've also seen it next to the original fuel nozzle that it replaced, and it's pretty impactful because the fuel nozzle that's 3D printed is very elegant and sleek looking, and the one next to it, the 20-piece welded monstrosity, is hideous, all right? So just visually, if you might ask, why do I care about 3D printing? All I have to do is show you that picture, and now you get it. Oh yeah, that's a big deal, okay? So I wanted to use that. I've seen that picture somewhere, and I wanted to use it in the class I taught last semester. So I went online to find the picture, and I couldn't find it. That's a little bit weird, but I'm also a 66-year-old man, and maybe my Google skills are a little lacking. So I asked my grad student to find this picture. I've seen it before. It's a black and white picture with two fuel nozzles side by side. And she can't find it either. So now this is really getting kind of weird. And there's people on campus all the time, parents and students, high school students visiting. I'm always poaching a little bit or recruiting a little bit. And so happened about a year ago, the family I was talking to, the dad worked for GE. And he said, yeah, I've seen that picture, but it's never been released for public consumption. So apparently I didn't see that on the internet. I saw that in some presentation. I think I was at Wright Patterson Air Force Base in Dayton, Ohio, years ago, when there was a GE engineer making a presentation. And I think that's where I saw that picture. And I asked Dad if I could get a copy of the picture, and all I've heard so far is cricket noises. So yeah, they're not happy about that getting out for whatever reason. But if you saw that picture, you would understand the lure of 3D printing, but specifically to your point. So now the 3D printing process, I can make a channel inside that nozzle that does the necessary geometric swirling to get the better fuel efficiency. So I got a 15 or 20% boost in fuel efficiency by using this new nozzle. Right? That's a big deal. Fuel costs are a big part of a big deal for airlines. And then more importantly, GE can't print metal parts and stick them on commercial engines or commercial hardware unless they get FAA approval, right? They're the watchdogs. We're looking out for our safety, and we don't want GE to get too far ahead of themselves and have something go wrong and have there be an accident, right? So the FAA is always looking over their shoulder, and the FAA gives them approval to print this nozzle, and that's it, because the FAA knows the strength's not very good, and GE knows it too. They just won't admit it out loud. And so the fuel nozzle is a perfect choice because it doesn't need strength. All it does is squirt fuel, right? So for 2024, it's a perfect choice. It allows me to make a complex shape I couldn't normally make to get the benefit of the fuel efficiency, and the fact that the strength is awful is not a detriment. So go for it. But that's as far as it goes until GE can make a more robust part. We're not going to see fan blades being printed for a while, I don't think. Again, that's to the metal science guys and gals to figure that out. So that's the next hurdle. Got to get the strength up, or it's still not going to go very far. And you don't know this, but old guys like me remember that in the early 80s, powder metallurgy was a huge thing. Powder metallurgy is, so let me back up. If I have a big part I want to make, and I'm going to go to the foundry and pour it, the downside to a casting is what solidifies first on the outside is going to have different chemistry than what solidifies last deep on the inside. So I have a non-uniform chemistry, and there's that non-uniform mechanical properties, all right? You got to live with that if that's what you do with cast parts. Powder metal gets away from that problem. Now I'm going to take metal powder, and I'm just going to heat it up and squeeze it together, and I can make my part that way. Heat it up, squeeze it together, and now I've got a part, and it's going to have uniform chemistry, so it's going to have uniform mechanical properties. So powder metallurgy in the 80s was a big deal. It changed the way we do things, and everybody's excited about it. And so we chased that technology then, just like we're chasing 3D printing today. But we got a little ahead of ourselves, and the Air Force put a rotor on a jet that was powder metal, and it broke. And the momentum of the powder metallurgy thrust just completely collapsed, all right? When you have a visible failure with new technology, it's not good. The investors pull out, and so powder metallurgy never really lived up to the hype and never really recovered from that little stumble. And so an old guy like me remembers 1982, and so we got to make sure we don't make the same mistake with 3D printing. We want to put those parts out there until they're ready, because if there is a failure, all this momentum that I've been hyping is just going to evaporate. You know, it's just a cautionary tale. Yeah. Yes.
Have you ever seen where they use the paste for 3D printing instead of the powdered metal?
I didn't hear the first part.
Paste for 3D printing.
I've never seen that for metal, no.
I was in Chicago a couple weeks ago.
Okay.
And they were doing plastic injection mold core blocks.
Okay.
And they started teaching how to make paste.
Really?
They gave you some information.
Yeah, I'd like to see that.
And when they heated it, it melted out that binder, right?
Yeah.
Okay.
So you get some part shrinkage, of course.
Yeah.
But they were using a special kind of binder to hold that metal together.
Okay.
And then once they sintered it or put it in the oven and cooked it, it melted that out.
Nice.
And it was really interesting because you're talking about the path for that engine.
Yes.
Well, plastic injection, you're trying to get a cycle time. Might be 40 seconds, 50 seconds to do a part. What they were able to do is do these crazy water lines by 3D printing.
Okay.
And they could reduce the cycle time by 40 parts, or 40%, which when you're making 1 million parts,
It's a big deal.
huge.
Yeah. Nice. There's a lot of innovative manufacturing things going on. Yeah, and understanding the metal's response to heating and cooling and pouring and forging and all that's pretty important. Yes.
Going back to what y'all were saying, there's a thing where you can do just with any 3D printer. You print, I think it's like 80% metal, 20% plastic. You can make a print and then you can kind of like form it around, or like pack sand in it. You can put it in a foundry and you like slowly heat it to where you melt the plastic and the metal, and then you crank up the heat a lot and it burns off the plastic, leaving just the metal. And you can do it with really any 3D printer. You just need some special parts. I've done it to make little like homemade rocket engines. It's not very precise, but you can get a solid metal print out of it.
Is it legal to make rocket motor engines?
That's kind of what I was going at. I was thinking, okay, Rocky's going over here.
But then, can I ask you a welding question?
Yeah.
So I'm a machinist by trade, so I don't really understand all the welding technology, but, I mean, we weld aluminum,
Yes.
we weld steel, we
Yes.
weld stainless,
Yes.
and those materials have different atomic structures, like body center cubic and face center cubic. And so what is it about certain metals that you can't weld? You have to wind up, brazing it or something like that. Why is it there's certain metals that cannot be welded by a traditional process? Whereas, we have all these different, like aluminum is a very different metal than, steel.
Yeah.
But both of those can be welded. But there are metals that don't lend themselves to welding. It can't be just atomic structure. It's got to be some other factor.
Yeah, so let's talk about steel. Some steels can be welded and some not so much, right? And so, but they're still steel. And so, a high strength steel, when it's cooled quickly, like the cooling that occurs during welding, when it's cooled quickly, the alloying elements give me different phases of when a weaker, more structural steel as well. That's not making a lot of sense. I've got two steels, and one of them is going to form different structure during solidification than the other, and that different structure is going to give you the lack of strength and the brittleness and the cracking susceptibility. So I'm trying to speak without using metallurgical jargon. Do you know what martensite is?
Yes.
Okay, so that's what I'm talking about. A high-strength steel, when it's cooled quickly, is going to form martensite, and that's going to make me prone to cracking. And then if I've got an A36 steel, I'm not going to get that martensite. If I do, it's going to be very much less hard than the higher-strength steel. So I'm going to get different mixes of I'm going to get martensite versus pearlite and ferrite.
So the whole idea here is not that it can't be welded, but the welding is not going to be successful because of the way the cooling is happening and the alloy content and things like that.
Yes.
So high carbon's a problem
Carbon's a big problem.
so the higher the carbon content, the more difficult it is to weld.
Absolutely. You're going to be much more prone to some martensite formation as you crank up that carbon content.
For material like, I know this is because I know it, not because I weld it, but like 304 stainless.
Yep.
You can get an L version.
Yep.
Welds better. And what is that? Is that a
Low carbon.
low carbon?
Yeah, and that's primarily because that's an austenitic stainless steel, and when you weld on it, you're going to get, if there's carbon in there, it's going to combine with the chromium on grain boundaries, and you're going to deplete an area along that grain boundary of chromium, and now those grains might fall out. And so you need low carbon so that you don't form chromium carbide and steal chrome from the grain itself. So that the element is low carbon. As an austenitic stainless steel, you're not going to get there's no martensite being formed. It stays austenitic all the way down from elevated temperature to room temperature. You just need to get the carbon out so that you're not going to have that grain boundary.
And the nickel is acting as austenite.
That's correct. Nickel does the austenite promoting, and then chrome does the ferrite. I think I'm getting that right. You have chrome and nickel, they're doing opposite things. One giving you ferrite, one giving you austenite, and I'm starting to wander away from my area of comfort. Yeah. And some things just can't be welded. You know, I went on Monday, I went to Huntsville and recruited, and I was at the Rocket Center. And I don't know if you've been there before, I've never been, but they've got a lot of, NASA hardware in there. And they've also got a V2 rocket. You know what a V2 rocket is? Who knows what a V2 rocket is? What's a V2 rocket?
It's the rockets, the Germans,
Yeah, so they're shooting rockets from France or Germany or wherever at London, right? They're the first people to have these long-range rockets. And so they have one of those rockets in the rocket center, and it's a little bit dimpled and dented, and it's no welds, it's all riveted, all right? I'm not sure why that is, but the airplanes today are almost all riveted. There's no welds on a commercial airplane because the aluminum alloys they use don't respond well to welding. So some aluminum alloys you can weld, some you can't. And the aircraft grade aluminums that have the strength that they need, weldability is not good. So you still see rivets. You might think eventually we're going to be done with rivets. It seems pretty barbaric, old school, but yeah, they're still out there.
One of my former students worked on an aircraft carrier as a I don't know what they call that repair guy. If they have any kind of structural damage to that plane or anything needs to be repaired.
Yeah.
And he said those rivets, the skin of the aircraft is aluminum.
Yep.
He said the rivets would come in packed in dry ice. They were going to put them in cold.
Okay.
So they put them in cold, and then when that plane is moved out to the flight line or out on the deck, with it heating up, it actually makes that rivet harder.
Stick it in there harder.
Yeah, it actually strengthens up that rivet after they put it in.
So if you open up a material science, so going back to World War II now, Germans had some pretty sophisticated engineering. That V2 rocket, that's something that the U.S. did not have. The Germans developed the first jet plane towards the end of the war. We didn't have one of those either. Their tanks are better than ours, so those guys do some good engineering. And one thing the Germans also had at the beginning of World War II was submarines. I talked to you about making submarines. The Germans had a lot of submarines, and they were terrorizing ships leaving the U.S. and going to England to drop off supplies. And so these Liberty ships were the first welded ships to be mass-produced, and they had some welding-related problems, and some of these things were cracking catastrophically. And if you open up any material science book, somewhere in chapter 1 is a big picture of a fractured Liberty ship, because we didn't do a good job with our welding consumables weren't very good at that time, and we didn't have the knowledge we have today. So that transition into welded ships didn't necessarily go very well, and you always see that documented in a material science book. But what you don't see documented is, those ships were breaking because the welding technology wasn't very good. But those ships were also getting shot at by German U-boats, right? Shooting torpedoes at them. And I went to Chicago for one of those foundry visits. There's a museum there where they have a German U-boat inside a building, believe it or not. And there's lots and lots of welds on that ship, on that submarine. Why don't I ever hear about German submarines breaking too? Because I sure hear a lot about Liberty ships breaking, and these are occurring at the same time. Those U-boats are being fabricated. So we're making our Liberty ships. What's different about a sub versus a ship? I don't have an answer, but that's a bit of a mystery to me. All those submarines were stick welded, and the welds looked pretty good, but they didn't look like magically good. So I don't know if the Germans had trouble with breaking and they just kept it to themselves and didn't advertise it, or they were dealing with a better steel than what we had. I really don't know the answer. But we had a lot of Liberty ship failures that we still talk about, and we don't talk about U-boat failures. Weird stuff. But I did learn is So when those submarines, those German submarines needed maintenance, they went to shipyards in France, because France was occupied by Germany. And so the French workers would drill holes in the submarine where they knew oil would leak, and they'd fill up the hole with wax and then paint over it. And then once that sub was out in the ocean and the wax came out, then oil leak would ensue, and an oil leak is the only really reliable way for you flying in an airplane to locate it where a submarine is. And once it's underwater, you can't see it, but you can sure see the oil slick that's leaving behind, it's leaking oil. And then they can drop their torpedo bomb on them and dive bomber and try to take the sub out. So that's a cool story. If you leave me up here long enough, I'll just keep rattling on stories. I would not want to be inside that German submarine, it's pretty cramped. Yeah, that's not good.
Any submarine is like that.
Well, I guess, yeah, so I guess I'll wrap it up. I'll reach out and see if we can organize a family trip. Yeah, I think you'll be impressed by that. And it'll give you a chance to visit campus and maybe give you a chance to go check out Bryce Hall. Really, really super awesome. Yeah. Good. I'm going to leave you with a handful of business cards. And if any of the students, he's going to have some of my cards. If any of you want to reach out with an email, I encourage you to do that. If you want to come to campus sometime and get a tour of some of the equipment that we have, you're happy to do that. I do it all the time. You want to do that? Yeah. So he's got my card with an email address. I don't really answer the phone, that's on my card, but I definitely answer email. And so we're happy to chat with you and organize a visit if that's what you want to do. Yeah.
Any last questions to wrap up? We want to thank you, sir, appreciate you taking time.
Absolutely. Yeah.
And we'll see if we can come on boundary and maybe a little field trip.
Yeah.
See your laboratory.
Absolutely. Yeah.
Thank you so much. Very good, sir. Thank you.
All right.